So good day, everyone. So today we're going to discuss chapter 8 in the University Physics with Modern Physics by Young and Friedman, 14th edition. So this is chapters entitled about momentum, impulse, and collisions. We're gonna include also here the center of mass and the rocket repulsion. Okay. In this chapter, you will learn, okay, just wait for a minute. In this chapter, you will learn the momentum of a particle and how the net force acting on a particle causes its momentum to change. The circumstances under which the total momentum of a system of particles is constant are conserved. So we are going to learn also the types of collisions such as elastic, inelastic, and completely inelastic collisions. We're going to discuss and have an example of these collisions in one dimension and two dimensions. What's what's meant by the center of mass of the system and what determines how the center of mass moves, okay, and how to analyze situations such as rocket repulsion in which the mass of an object changes as it moves. Okay, if the first topic here is about the momentum of a particle. Okay. So what is the momentum of particle? That's the definition. This is a physical quantity. This is a vector. It has magnitude and direction. Okay, the momentum of a particle is a vector quantity equal to the product of the particle's mass and velocity. So meaning, it follows that this momentum, that this physical quantity is the same direction with the velocity. So in the equations, the momentum is just equal to the mass of the particle times the particle's velocity. In the diagram, you can see that momentum and velocity has the same direction. Okay, so how did we derive this equation? How did we derive this momentum? Okay, if you recall, we have the Newton's second law. Okay, okay. So let's go to the Newton's second law first. Okay. How did we derive this one? So if you recall that the Newton's second law, I mean, states that the net force, okay, if the net force is acting on an object, then that object with mass m will accelerate. Okay, this is the equation for the Newton's second law. Okay, we know that the acceleration is just equal to the derivative of the velocity with respect to time. So this is equal to m, okay, dv over dt. Okay. So we can put this m inside the derivative. So we have d of m over dt. So if we let p, small letter p is equal to mv, we call that one as the momentum, then the Newton's second law in terms of acceleration will become now the Newton's second law in terms of momentum. Okay. So mv here is the what we call the momentum of a particle. Okay. So from this equation now, we can now equate the Newton's second law in terms of momentum. Okay? The net external force acting on a particle, this is equal to the rate of change of the particle's momentum. This is what the Newton's second law in terms of momentum. Okay. So let's go to another physical quantity called the impulse. So we define now the momentum. Let's define now the impulse. So what is the impulse? What is this physical quantity? So if a constant net force, okay, it involves again the constant net force. acts on a particle for a time interval t1 to t2, then the impulse j, this is a physical quantity now, a new physical quantity denoted by j. It is a vector. It has magnitude and direction also. The impulse of the net force, the net external force, is the product of the external force and the time interval. So the impulse, okay. So if the net force is constant, the net external force is a constant, the impulse is just equal to the net external force times the time interval. Okay, the time interval over which that external force acts. Okay, that's the definition of impulse. So how about, sir, if the the net force varies with time? Okay, if the net force is not constant, then the impulse j is the integral of the net force over the time interval. Okay, so the impulse in a general net external force, either constant or either varying, is equal to the integral of the net external force over the time interval. Okay, we have the lower limit, the initial time, the upper limit, the final time, and we have the time integral of the net external force. Okay, in application that of this impulse, this physical quantity, if you're familiar with a woodpecker, okay, uh, the woodpecker has been known to strike its beak, it can strike its beak against the tree up to 20 times a second and up to 12,000 times a day. So it's very many times. Okay. The impact force can be as much as 1,200 times the weight of the bird's head. Because of the impact, less lasts such a short time, so very, very fast, like this. Okay. The impulse, the net external force during the impact multiplied by the duration of the impact is relatively small. Okay. The woodpecker has the thick skull of spongy bone as well as the shock absorbing cartilage at the base of the lower jaw, so it avoids injury. Okay, so remember, do not wag niyong gayahin si woodpecker. Do not imitate because we don't have this structural capability in our head. This is special to them. Okay, so that's the application of the impulse. If you apply a force, the external force is acting on something over a time interval. So you multiply that one, that's the impulse. Okay, are the impulse and the momentum related to one another? Okay, so actually they are. Here we have the impulse momentum theorem. So in any case, actually either the net force is constant or not constant, the change in the particle's momentum, which is if the momentum changes during a time interval from P2 minus P1, okay, the final momentum minus initial momentum, or the change of momentum, equals the impulse of the external force that acts on the particle during that interval. Okay, the momentum of a particle equals the impulse that accelerated it from rest to its present speed. Okay. So do you think, do we need to derive this one? J impulse is just equal to the impulse of the net force over a time interval is just equal to the change of the particle's momentum, meaning the final momentum minus the initial momentum. Okay, say for example, a constant net force. Okay, if this is constant, then yeah, so in terms of the Newton's second law, so if this is constant, then this the 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 rate of change of the particle's momentum is equal to this one. Only if constant. Okay. Is equal to the change of momentum, the this one, the final momentum minus the initial momentum over T2 minus T1. So if we multiply this both sides by the time interval, which is T2 over T1, so we have the net force in the other side times the time interval, and we can cancel this one. So we have the change of the particle's momentum. Okay. This one term is just J. So therefore, this is equal to the impulse J. Okay, the impulse J is just equal to the change of the particle's momentum. Okay, how about if it's not constant? The net force is not constant. Okay, if the net force is not constant, then the impulse J is equal to the integral from T1 to T2. That's the if this one is not constant. Okay, so what we're going to do is that from the Newton's second law in terms of momentum, so we have dp over dt. Okay, since we can cancel this one, and since this is the integral in terms of momentum, we can change the limit, the boundary condition. I mean, we can change the upper limit and the lower limit by momentum. Okay, since this is p, it can now become p2, p1 over p2 dp. Okay, so this will become p2 minus initial. Okay, so that's what we call in any cases, whether constant or not constant, the impulse is equal to the change of the particle's momentum. So in a real world, forces are variable. Okay, forces acting on object often change over time, such as collisions or varying interactions. Okay. So instead of dealing with the fluctuating force, we define now an average force to represent the overall effect over a time interval. So we define F average such that the impulse J can be expressed as the F average over the time interval. Okay, it provides us an easier way to compute the impulse even when forces are not constant. Okay, for the special case, for example, that the net force is constant, then the F average is equal to the net force, and this equation will go back to this equation like this one. Okay. So we define now that F average to represent the effect of over the, I mean, to address the fluctuating uh, values of the average force. Okay. So this example 8.1, I will ask you to study this one. I will not be discussing that one here because that's a reading assignment. Okay. So let's apply those concepts to what we call this one problem. Okay, so remember, impulse are vector quantities. It has a magnitude and direction. Okay. So example 8.2, the ball hits the wall. Okay. So you throw a ball with a mass of 0.40 kilograms against the brick wall. Okay, you throw this one against the brick wall. Okay, this is our positive direction. This is our negative direction. It's moving horizontally to the left with 30 meters per second when it hits the wall. It rebounds horizontally to the right at 20 meters per second. Okay, find the impulse of the net force, external force on the ball during its collisions with the wall. If the ball is in contact with the wall for 0.010 seconds, find the average horizontal force that the wall exerts on the ball during the impact. Okay, so let's recall first what we have learned. What are the concepts that we have learned? We have the impulse momentum theorem, which is equal to the change of the particle's momentum. This is the impulse, this is the final momentum minus the initial momentum. Since this is a vector quantity, we can express this one as in component form, which is P2 x minus P1 x I hat plus P2 y minus P1 y, okay, j hat plus P2 z minus P1 z, okay, k hat. So here this is equal to jx I hat plus gy j hat plus gzz k hat. So this is now the impulse. Okay. Since this is problem is just one-dimensional along x, so the x component, this is just the one-dimensional problem. So we can just use this term here. Jx is equal to the P2x minus P1x. Okay. So particularly, this is equal to m, the mass of this object. Then we have, because this is the final momentum, V2x minus m v1x. Okay, m v1x, like that. So find the impulse. If you want to find the impulse, so you can actually factor out the m v2x minus v1x. So we have here the initial, which, okay, the initial, which is the we have there the final values. So the ball went to the wall and then bounced back. This is before and after. So we have the mass of the ball, which is 0.40 kilograms. Okay. Multiplied by the final, which is positive, minus 30 meters per second. Negative. Maybe I'm gonna put this one right here. Times 20 meters per second minus the negative 30 meters per second. Okay. So what is the impulse? Can we calculate? Let's do the calculation together. 0.40 times 20 minus negative 30. So we have 20. Okay, we have 20. So the unit of this is, since this is force times the time interval is Newton per second, or we have kilograms meters per second. Okay. Or we can write this one as 20 Newton per times seconds. Okay. How did it came to this unit? Okay. If we look at 1 Newton is equal to 1 kilograms meters per second squared. Okay. 1 Newton is equal to kilograms meters per second. Therefore, 1 Newton per second is equal to 1 kilogram meters per second. Okay, that was 1 Newton. So this kilogram meters per second is equal to 20 newtons per second. Okay, so the impulse, the magnitude, the impulse is equal to, this is for letter A, is equal to that value, 20 Newton per seconds. Okay, for letter B, it has a question for letter B. find the ball. Find if the ball is in contact for 0.10 seconds, find the average force that the ball exerts on the ball during the impact. Okay. So the F average. So from this equation, okay, if you recall this one, so you're gonna write this one F. Okay. Along the x component, Jx is equal to F average along x times the time interval. Okay. So the F average is equal to the Jx over the time interval, which is the time interval is just 0.10 seconds. So we have 20 Newton per seconds over 0.010 seconds. So divided by 0.010. So about 2000 so Newton. Okay, that's the okay. So if you're gonna be hit by the 0.40 kilogram, almost a half kilos of ball, which is traveling of negative 30 meters per second, you're gonna be hit by a 200 Newton, provided that it bounce back at positive 20 meters per second. Okay, how about that two-dimensional problem? Do you think? So here I say kicking a soccer ball. Okay, this is a two-dimensional problem. Okay, a soccer ball has a mass of 0.40 kilograms. This is initially it is moving to the left of at 20 meters per second, but then it is kicked. After the kick, it was moving 45 degrees upward and to the right with a speed of 30 meters per second. Okay. Find the impulse of the net external force and the average net external force assuming a collision time is 0.10 seconds. Okay. So two-dimensional, again, this is 2D, there's no z-axis here. We can use this equation. Okay, I'm gonna recall this one, that the J is a vector quantity, which is equal to this one, the final minus the initial momentum. Since this is a vector quantity, so we defined already last time that this J in terms of momentum is equal to P2x minus P1x, okay, I hat plus P2y minus P1y j hat plus there's no z component, so this is gonna be 0. I will not gonna write it, but it is three-dimensional collisions, I'm gonna include that one. Okay, here is just a two-dimensional collisions. So here this is equal to jx I hat plus jy j hat. Okay. So now, uh, for the letter A, after find the impulse of the net external force, you're gonna find the impulse J. So to do that, you can actually find first the components Jx and Gy, then uh, you can you can do find the magnitude, okay? But in this problem, this is a vague. It's not state clearly if what is being asked is the magnitude of this one or just the components. Let's see. Moving to the left. After it's moving forward speed, find the impulse of the net external force. Only the impulse. So let's assume that gonna find the magnitude as well as the direction of the impulse. Okay. Let's just assume that. Okay, so in the x component, jx, this is equal to the p2x minus p1x. This is equal to m v2x minus v1x. Okay. Jy, or we have m v2y minus v1y. Okay. So, so the problem now is finding the values of v1x, v1y, what are the values of this, and uh, v2x and v1y. What are the values of this? Okay, let's analyze. So we have the magnitude. So if we draw a Cartesian here, okay, the the vector v1 is along that direction. That's the velocity vector v1. Okay, it has no y component, obviously. So this is equal to 0 because uh, the sine of 180 degrees is equal to 0. If you're gonna insist to show that one is equal to v1, so from the x component, so v1 is 180 degrees, so v1 sine 180 degrees is equal to 0. And this one is also v1 cosine 180 degrees. This is equal to the negative 20 meters per second. Okay. So why? Because this is negative 1 and this one is 20 meters per second times negative 1. Okay. How about the y class? How about the the v2x and v2y? So here, this is the vector v2. It has a magnitude of 30 meters per second. You can find it has 45 degrees. Okay. It has components vx and vy. So since you're going to use the angle from the positive x-axis to the vector, so meaning the x component is automatically cosine. Okay, cosine. So we have 30 cosine of 45 degrees. Oh, let me. So 30 cosine 45. So we have 1.2. So since this is not a final calculations, let's actually have many digits. Let's carry extra digits, meters per second, and the v2y is equal to v2 sine 30 degrees, so which is equal to 30. It has a meters per second. Okay, 30 meters per second cosine 45 degrees. So what is the value of this one? Is that cosine or is that sine? This is actually sine because it is the y component. So we have the same. So we can now find the values. This is positive. So so the mass is 0.40 multiplied by this one, what is V2x minus negative 20 meters per second, and the other one, the V2y is 21.2132. Let's add to here, minus 0. Okay, so here that Jx is equal to, let's calculate together, 21.313 minus negative 20. So let's, we have 16.53, 16.53. The unit is kilograms meters per second. So why are we not why are we not obeying the rules in determining the significant figures of the result? Because this is not yet final. So it's, if the calculation is not final, it's good to have an extra digits. 40 times 21.232. So 8 point. So this one is 2 1. So 8.485, 3 kilograms meters per second. Okay, so let's find now the direction. Okay, let's find the direction and the magnitude of J. Okay, so J, the magnitude of J is just equal to the square root of the components. Jx squared plus Jy squared, which is equal to the value of this one. Okay, square root of 16.53 squared plus 8.4853 squared. So we have 18.6 Newton per second. Okay. So the direction, we can also find the direction of this theta here, but I guess we're not gonna include this one because it's gonna be included. It's the same direction as the force. Okay. Let's include na lang. Okay. So if if we graph this one, so Jx is positive. We have Jx, and Jy is also positive. This is Jy. So meaning the vector lies in the first quadrant, and if you want to this angle theta, so theta is equal to the opposite over the tangent of the opposite. What is the opposite of this is Jy over Jx. Okay. Shift tangent of Jy, which is Jy is 8.4853 over 16.53. About 27.2 or 27 degrees in two significant figures. In two significant figures, 27 degrees. Okay. So if you're gonna calculate the the direction of the force have the same direction of the impulse, this must be 20, the force direction must be also 27 degrees. Okay. So 16, 8.5, 16.5, 50. Okay. So let's calculate now so since we assume that our final answer is this one. So our J should be in three significant figures about uh 1.9, okay, or 19 Newton per seconds. 19 Newton seconds. That's our magnitude of J. That's- So that is our assumption. Okay. 1900. Okay. So what is now the average force, net external force, assuming that the collision is this one? Okay. Actually here, pwede na we can actually, so for letter B, since we get the magnitude already, the magnitude of J is equal now to, we can actually this one, uh, the magnitude of the F average over the time and times the time interval. Okay, we can actually calculate this magnitude of this, which is the magnitude of our F average of is equal to the magnitude of J, which is 1.9 Newton per seconds over, okay, this is thus the magnitude of our impulse over the time interval, which is 0 point, which is 19 Newton per meter, Newton per seconds times 0.010 seconds. The significant figures, 19 divided 0 point is 1,900 Newton, okay, or 1.9 times 10 to the 3, 3 Newton, because can cancel this one, cancel. So that is the magnitude for the direction. Theta is equal to 27 degrees also, like this one, or 27.1 or point 2. So that's the direction. This is for the direction. Okay. However, in the book, so what the books did is that define the components first, which is equal to Jx over the time interval. So our Jx here is 16.53 Newton per seconds over 0.010 seconds. So 1653 Newton, and F average along Y is equal to Jy over the time interval, which is from the previous is 8.4853 divided by 0.010. So we have 8.848.53 Newton. Okay. So to get the magnitude, okay, the magnitude of F, square root of 1653 Newton squared plus 848.53 Newton squared. So we have 18.1 Newton. Okay. But the final answer here is in two significant figures. So 1.9 times 10 to the 3 Newton. Okay. And the answer is the same with our. So why did we carry extra significant figures, extra digits? Because as long as it's not yet final, so it's better to have extra significant figures or extra digits so that your answers will be accurate. Okay. So only the final answers you express the the numbers of your results to the numbers of significant figures. Okay. Just like this one, we add figures. So here, what you do next, if you want to find the direction, this one, theta, so positive, positive, theta, the tangent of theta is equal to -1 of f average along y over f average along x. Okay. So if you use this value, shift tangent -1 of, so y is 848.53 over 1653. Okay, the same. So into significant figures, 27 degrees or 27.12172 like that, but into significant figures, 27 degrees. Okay. So here we assume that our final answer is this one. So two significant figures, two significant figures. Okay. So we assume that our final answer is must be into significant figures. Okay. So thank you for listening. Hope you enjoyed our lesson. It's time now for our 5-minute break. So the 5 minutes break is done now. I hope you stretch, relax. Okay. So today we're going now how right now we're going to discuss conservation of momentum. Okay. So before we discuss the conservation of momentum, let's define first what is the meaning of internal force. So the internal force is the force exerted by one part of the system to another. So say for example, we have two astronauts. They are in the environment of space where there's no gravity, there's no friction. So there are no other forces but the forces they exert from one another. These forces, we call that one as the internal forces. Like the force exerted by the astronaut A on B and the force that the astronaut B exerted on A. Those forces are called internal forces. Now, what are the external forces? Okay. So the external force on a part of the system, external force is a force exerted on any part of the system by something outside the system. Okay. Say for example here that ice skaters push each other as they skate on a frictionless horizontal surface. Okay. So right now, although they are no longer in space, they are no longer in an isolated system where the net external force is zero. They now have the normal force, the the weight force. Okay. So gladly they were in the ice. There's no friction. This is frictionless. But the normal force, the weight force, are those forces that we call external forces, where it was exerted on any part of the system by the outside system. Okay. So those are the normal force, and the internal forces here, those are the external force, and the internal force in this case is the force B on A and the force A on B. Okay. So we come now to the conservation of momentum. So what this conservation of momentum means? Okay, it means that if the net external force on the system is zero, the total momentum of the system P. Okay, we define now a, a new vector quantity, physical quantity, which is the total momentum, which is the vector sum of the momenta of the individual particles up the system. Okay, if the net external force of the system is zero, the total momentum P is conserved or constant. So what do you mean by this? Okay, so let's look at first here. Since this is an isolated system, meaning there is no force, external force acting on them, only internal forces, it says that the total momentum P, they have before total momentum P is constant or conserved. Okay. In B also, since although they have external forces, but if you add them up, if you add them, it will just result to the net external force are zero. Kung imo siyang i-add tanan, they're gonna be zero. So meaning, in these both cases, all the external forces are zero, and both of these cases, the total momentum is conserved. Okay. So meaning the total momentum of the systems of particles, like not just two particles, but three or more, then the total momentum is just equal to the momentum of particle A plus the momentum of particle B plus equals like this. Okay, the equals vectors sum of the momenta of all particles in the system. Okay. How is it useful, class? Okay, okay, let's talk about this further about this. Uh, if you look at this one, Newton's third law, they exert on each other. Okay, force A and B is, for example, this is positive, and force B on A is negative. Okay, let's look at what this really means. And okay, this for example, this one. So you have two system, F A A on B is equal to the negative F B on A. If you're going to add the system, add their forces, this from the Newton's third law, action reaction force, A on B plus F B on A, this is equal to 0. They have the same magnitude but opposite in direction. That's why if you add the vectors A and B, I mean, you can actually write this one like this. F B on A is equal to the negative F A on B. So since if you add F A on B plus F B on A, since F B on A is just the negative of A on B, then that will become to zero. So Newton's second law in terms of momentum, this one is will become F the FB on A is just equal to the momentum of A on with respect to time, and this one F A on B is equal to the change of the momentum of B with respect to time. This is the force A on B. So this is the momentum of B with respect to time, the change of momentum of B. FB on A is the change of momentum of A with respect to time. So this is equal to zero. So here we have the momentum A respect to T is equal to the moment plus dP is equal to zero. So what do you mean by that? Okay. So if the total momentum of this system P is equal to PA plus PB, so this will be, so this here will become like this. The total momentum is equal to zero. Okay. So the derivative of the total momentum is zero, meaning P is meaning P is constant. Okay. So how is this useful? Actually, this conservation of momentum. How can you really apply this one? Okay. So we've shown you the proof that if the net external force is zero, we just consider the internal forces. We've shown that the derivative of the total momentum, which is the sum of the momenta of of these two, is equal to zero. Okay. So before collisions, actually, meaning, okay, okay, so for example, we have two systems colliding. Okay. We have, so can we have like this. I'm gonna put here like this. So before collision, sorry. So before collisions, uh, we have here A and we have B. By the way, collisions are momentum of collisions are conserved. We're gonna discuss this one later. So this is during. Okay. This is A and it's B, and this is A and B after. Okay. So before, so for example, they are about to collide, they have velocities towards each other, and during they collided now, and after they have now final. So instead of two, we're gonna use uh, VB, for example, and this is the initial VA. Okay, so after the collisions, they have now V prime and VA prime. So just for example, so here they have an initial total momentum. Okay. Uh, VA plus, ah, I mean, they have initial momentum, VA plus VB. Okay. After the collision, they have a final momentum like this, VA prime plus VB prime. Okay. Okay, in collisions class, by the way, I'm just gonna tell this right here, is that the internal forces is too big compared to the external forces. That's why we can treat this one as an isolated system where the total momentum P is conserved. Okay, so what do you mean by conservation of total momentum? So it means that as long as the external force is zero or negligible, if the value of your total momentum here must be the same of your total momentum after. So meaning your total momentum before initial is equal to your total momentum after or final. This is initial is equal to final. Final total momentum. So that is the application of this conservation of momentum. So your is the meaning constant. What is the value of the total momentum from the initial is also the value of your total momentum after the collision. Okay. So let's apply this conservation momentum to a problem. Okay. So this is a recoil of a rifle. Okay. So a marksman holds a rifle of mass MR of 3.00 kilogram loosely, so it can recoil freely. Okay. He fires the bullet of mass 500 grams, 5 grams, horizontally with a velocity relative to the ground of VBX is equal to 300 meters per second. What is the recoil velocity of the rifle? What are the final momentum and the kinetic energy of the bullet of the rifle? Okay, so we're not gonna obey the notations or what are being used by this book. We're gonna make another simpler equations. We're gonna use the prime, for example. Okay, so that we're not gonna write so many prefixes, so many subscripts like that. I mean, okay. So here, since we can treat this one as the momentum conservation. So if you want what is the final momentum and the kinetic energies of the rifle, okay. So here for the final momentum, let's treat this system as uh, the, the the total is conserved or constant. Okay, this is an example of conservation of momentum. Okay, so meaning the P initial is equal to the P final. Okay, so for the initial values, you have actually the the momentum of the bullet, and you have also the momentum of the rifle. That is your initial momentum. Final, also you have the final momentum, total momentum, bullet, final, plus rifle, final, just like that. Okay, so we can rewrite this one as like this. P, let's do the rifle first, plus P bullet is equal to P. Okay, since this is in the x-axis, this vector is only one dimensional. We can treat this one as a one dimensional problem. So we have P Rx plus momentum of the bullet along x is equal to the P, the momentum of the rifle x prime plus P bx prime. Okay, this is only one dimension. We only consider the x component. Okay, this is equal to m of the rifle mass the velocity of the bullet at the velocity of the rifle along x initial, m of the bullet, the velocity of the bullet initial is equal to the m of the rifle, the velocity of the rifle, the final, plus the mass of the bullet, the velocity of the bullet x final. Okay, so what does it mean? Okay, here, so before firing, actually, the VRX here is equal to 0, and the VBX here is equal to 0, because there's no velocities yet because it's not yet fired. So meaning, this term in the left side is equal to 0. So our target variable is the recoil velocity. This one, what is the recoil velocity? That's our target variable. Okay, if you transpose this one to the other side, what will happen now is it will become let's instead of this one, let's transpose this one to the other side. So we have the mass of the rifle, the velocity of this one, the rifle is equal to the mass of the bullet, the negative mass of the bullet because it was transposed, the velocity of this one, you're gonna divide both sides, the mass of the rifle. So we have now the velocity of the rifle, the recoil velocity, the final, is equal to the mass of the bullet, 5.0 times 10 to the negative 3 kilograms times we have the velocity of the final velocity over 3.0 kilograms. So how did it came like this? Okay, so take note that 5.0 grams. So take note that in 1,000 grams, there's this 1 kilograms. So you have 1, so you have 5 times 10 to the negative, cancel, cancel. About mga 0.00 like this. Okay, let's be sure. 0.205 kilograms or 1, 2, 3, 5.0 times 10 to the negative 3 kilograms like that. Okay, so we have negative times 300 divided by 3. So we have negative. Our final answer is negative 0.5. So in three significant figures, 100 meters per second. So that is our final answers. So this is how you use the conservation of momentum. So what are the kinetic energy of the bullet and a rifle? So I will leave that one as your exercise. So you have now the final velocities of the bullet and you have now the final velocities of the rifle. You can calculate each velocity or kinetic energies. You can also try to calculate the momentum, the final momentum, since this is equal to 0. And if you try to calculate the final momentum, should be also equal to 0 because the momentum is actually conserved. So meaning if the value of the total momentum here is 0, your final momentum also must be 0. The book You can verify that one in the book, but I will not include it here. I will leave that as your exercise. Yeah. So another example for the conservation of momentum is a ballistic pendulum. This is a collision type of collision. Okay. So why is the conservation applicable here? So take note that in any collisions, the external forces are negligible because of the in collisions, the internal forces are so big compared to the external forces. Okay, so we can actually use the conservation of momentum here. Okay, so we have mass of the bullet, mass of this. So let's read. Figure 0.19 shows a ballistic pendulum, a simple system of measuring the speed of the bullet. Okay, this is how you measure the speed of the bullet. The mass of the bullet is mb. It makes a complete inelastic collision with a block of wood of mass mw, which is suspended like a pendulum. After the impact, the block swings up to a maximum height h. In terms of h height, mb, and mw, what is the initial speed v of the bullet? Okay, so first, let's use the conservation of momentum from conservation of momentum of total momentum. The initial, so let's treat this one at this P is equal to P final. Okay, so we have here in the initial and we have here in the final. So let's treat this one at this point. This is our point, our event one. Our event two is along here, and actually we also have an event three. Okay. So from this event one, we have here and our event two, event one and two is that event one, okay, before the collision. Our event two, immediately after the collision. This is our event two. This is immediately after the collision. So our event one is before the collision. Okay. So our momentum here, initial, before the collision is that P of the momentum of the bullet. Listed this one as one-dimensional problem. Okay, so P of the momentum of the bullet plus the momentum of the wood. We're not gonna put subscript X anymore. So we have P B plus prime P wood prime. Okay. So we have the mass of the test and we have the velocity or the initial V1, initial MB plus the mass of the wood, the velocity of the wood is equal to the mass of the bullet, the velocity of the bullet final plus the mass of the wood, the velocity of the wood final. So here you can see actually that after the bullet was stuck in the wood, they have the same velocity, meaning the VB final is equal to VW final is equal now to just V final. Okay, so this will become, in the right hand side, MV plus M of the wood is equal to na final that one, V2. Okay. So our target variable here is to find the initial. So since the wood here, this one is equal to 0, the velocity of the wood is equal to 0 because the V wood is equal to 0. So we have in the right hand side, MV, the bullet, and the velocity of the bullet. Okay. So therefore, the velocity of the bullet is just equal to, we're gonna divide this one, is equal to MV plus MW over the mass of the bullet multiplied by the final velocity of the bullet plus the plywood or the wood. And we can also use the conservation of energy here. Okay. So our conservation of energy here is we have here at point 1, okay? Point 1 before the wood or the block of wood was lifted at point 1 at point 2. Okay. So at point 1 it has a velocity v2 prime v prime, and at point 2 it we treat v double prime is equal to 0. Okay. And the height here, y is equal to 0, and at point again point 2, the height y is equal to the h. Okay, from the conservation of energy, so what is it, the mechanical energy, the total mechanical energy, so we can write this one as that, like this. It's k1 plus u1. Okay, this is gravitational potential energy because the gravity is just doing work. K2 minus plus U2. So if you recall, uh, U1 is equal to mg, Y1 is equal to 0, and K2 equal to 1 half mv. In this case, double prime squared, this one is equal to 0 is equal to 0. So this one is equal to 0. The initial kinetic energy. So we have a combined kinetic energy. Actually, we have two masses. So the kinetic energy, so the M here is actually M is equal to the mass of the bullet plus the mass of the wood. At point 2, the velocity is equal to 0. Therefore is equal to 0. And at point 1, the height is equal to 0. This one, the gravitational potential energy is equal to 0. Okay, so K1 here at this point is equal to 1 half times the mass of the bullet plus mass of the wood, and the velocity in this particular example is this one, v prime squared. And here the gravitational potential energy at point 2 is equal to mg times the height h. So from this equation, okay, so we have 1 half m b plus m w v prime squared is equal to mg H. Okay. So here, again, M should be the same as this. Okay. So the M is mv plus mw times g times h. Because there is now the wood and the bullet stuck together. So we can actually this one and multiply both sides by 2. So we have the v prime squared is actually to 2gh, where the v prime is equal to the square root of 2gh. Okay. So we can now get the velocity of the bullet. Okay. So the velocity of the bullet is just equal to the mass of the bullet, the mass of the wood over the mass of the bullet over v prime. Since v prime here is equal to the square root of 2gh, as we have discussed, so the velocity of the bullet now is equal to mass of the bullet plus mass of the wood over mass of the bullet times the square root of 2gh. So this is how you determine the the velocity of a bullet. So this is what they do to determine the velocity of the bullet. Okay. So if you are given the masses of the bullet and the wood, you can actually calculate the velocity of the bullet. Okay. So for example, if you have a wood which is uh, so the bullet is just 5 grams, and if you have a wood which is 2 kilograms and you have the height which is 3 centimeter, you can actually calculate the VB. But we will not do it here. Be we're just gonna end here. So this is the formula of how you calculate the velocity of the bullet. Okay, you can also get the 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 final velocity of the bullet and the wood. Okay, the bullet or of the wood. You can get their final velocity. They have the same velocity using the square root of 2 times the g, as long as you know the height. So this is a very good sample. Thank you for listening. So let's have a break again, and we're gonna discuss the collisions in the next chapters. 1D collisions first, and then 2D collisions. Okay, the end for a 5-minute break. So I hope you have stretched, relaxed, because we're going to continue our discussion for 1D collisions. So okay, like we said in our previous discussions, so a collisions is an example of system where the total momentum is conserved. So because if the forces between the colliding objects are much greater than any external forces, as in the case of the collisions like we've discussed, we can ignore the external forces and treat the objects as an isolated system. So since this is an isolated system, in any types of collisions, the momentum is conserved and the total momentum of the system has the same value before and after the collisions. So we've discussed that one, that the initial is equal to the final momentum. Okay. So meaning, if you have this one, if you have the momentum initial of A plus the momentum initial of B, this is equal to the final momentum of A plus the final momentum of B. Okay. Final means there is a prime. Okay. So the book is using 2 for final, but we are going prime. We're going to use prime, superscript prime for the final indication that it is a final values. Okay. So meaning, in any collisions, you can use this one, MA, VAX plus MB, VBX. We're not gonna use the X component because we're gonna use the vector, VA plus MB, VB is equal to MA, VA prime, final plus MB, VB final. Okay. This is the conservation of momentum. In any types of collisions, uh, the the final, initial and final momenta are equal. There are three types of collisions that we're going to discuss here. The one is the elastic collisions between two objects. Okay. The initial and the final kinetic energies in this type of collisions are equal, also equal. And the initial and the final relative velocities have the same magnitude. Okay. Now, so this is the example of the elastic collision. Okay. So before the collision, after the collisions, so after the collisions, they have a different velocity, final velocity. So in these collisions, the kinetic energy is conserved. For the inelastic collisions, the two object collision, the total kinetic energy is less than the collisions before. Okay. So although it looks like this elastic, but if you really look at inside the system, if you calculate the kinetic energies before compared it to the final, you can see that it's not equal. Okay, the kinetic energy are lost in this kind of collisions. Also, the what we call completely inelastic collisions, where if the two objects have the same final velocity, the collision is completely inelastic. So just like the ballistic pendulum, where the wood and the bullet is stuck together and they have the same final velocities. Okay, so here in the completely inelastic collisions, kinetic energies are not conserved. Also, they have the same final velocities. And in all these collisions, the momenta are equal in final and initial values, meaning the conservation of momentum is applicable in any types of collisions. Okay, let's look at first the one-dimensional elastic collisions. Example 8.7. Okay, here the two gliders with different masses move towards each other on a frictionless air track. After they collide, the glider B has a final velocity of 2 meters per second. What is the final velocity of the glider A? How do changes in momentum and in velocity compare? Okay. Since this is a collisions, actually we can only determine if it is an elastic or inelastic after we calculated the kinetic energies. If it's equal, then you can say that the collision is elastic. But if the initial is not the same as the final kinetic energy, then we can say that it is inelastic. Okay. So for the solution for this one, okay, first, what is the final velocity of the glider A? Okay. So we use the conservation of momentum from so here we have the the initial total momentum is equal to the final total momentum. Okay, meaning we have glider A and B, the P A plus the momentum of B is equal to the momentum of A final plus the momentum of B final. So these are the okay, you can expand this one. Since this is only in the x-axis, we can focus on the x component only. So we have the mass of A, the velocity of A along the x, plus the mass of B, the velocity of B along the x. This is equal to the mass of A, the velocity of A prime, plus the mass of B, velocity of A final. So both have initial velocities. Our target variable here is find this one. This is our target variable. Okay. So to do this, let's rearrange this one. Let's put this one into the left-hand side. So we have, starting writing from this, the mass of A, the final velocity of A prime is equal to, copy this one, mass of A, the velocity of AX plus the mass of B times the velocity of BX minus, because you transpose this one, minus MB, the velocity of B prime. Okay, you multiply by MA. Okay, so we can write this one, our final equation, can write that the V, that this is equal to the mass of A, the velocity of the initial, plus the mass of B times the velocity of the initial minus the velocity of the final over the mass of A. So we can write this one. Pila atong mass of A is 0.5 kilograms times the velocity of A. How much is the velocity of A? Initial is 2 meters per second. It's 2.0. Maybe we're gonna go to the next slide. Okay. Let's skip this one. Copy. And let's make it smaller. This one too. Outside. Smaller. I'm gonna copy. Okay. So here, so we can invest something. Okay, here, our final velocity, AX prime, is equal to the mass of A, which is to 0.50 kilograms times the velocity initial, plus the mass of B times the initial velocity minus the final, which is 2.0 meters per second, over 0.50 kilograms. Okay, we can cancel the kilograms. So we're left with meters per second. Use our calculator. Plus 0.3 times -2 minus 2 over 0.5. So this is our final answer. So let me check first. It's consistent with our book. So we have negative 0. So in this negative 0.40 meters per second in three significant figures. So this is the final velocity of the x, or in our book, use this VA2x. Okay. How does the changes in momentum and in velocity compare? Okay. Okay. If you if you look at this one, let's look at the initial momentum. Okay. The initial momentum of A is equal to MA VAX, which is equal to 0. Okay. How do the change in momentum and in velocity compare? So maybe I'm not gonna include this one because I'm gonna leave this one as your assignment. Okay. What are we going to do here is just let's prove that, let's determine if this is, instead of doing this one, let's just determine if this is an elastic collision or inelastic collision. Okay, let's look at the kinetic energy. So the Ka plus Kb, the total, is it equal Ka prime plus Kb prime? Okay, that's the question. Is this, okay, Ka 1/2 times 0.5 times, what is this quad? 2.0 meters per second squared. So we have 1.0 joules for Kb. So the same method, one half times 0.3 times -2.0, 0.50 kg. This is 0.60 joules. Okay. Ka plus Kb is, so therefore this is 1.60 joules. And So our goal here is to, so Ka prime is equal to 1/2 times 0.50 kilograms times the, what is our answer last time? Is it negative 0.4 kilograms meters per second squared, 0.5 times 0.5 times 0.4 squared. So atong Kb prime is equal to 0.5 times 0.3 times 2 squared, 0.6 joules. Okay. So we have, this is equal to 0.64. Okay. So so Ka plus Kb is equal to 1.60 joules, and K prime plus Kb prime is equal to 0.64 joules. So meaning 1.64, so meaning the total initial kinetic energy is 1.60 joules, is not equal to 0.64 joules. Okay, so what's the meaning of this? The meaning of this, that the collision is inelastic. Some of the kinetic energy, there are kinetic energy lost. Okay, so that's the meaning of inelastic collisions. Momentum is conserved. It did not stick together like an completely inelastic, but there are loss of kinetic energies. Okay, I hope you understand what do you mean by that. So let's go to the completely inelastic collisions. So what do you mean by completely inelastic collisions? So meaning, in completely inelastic collisions, they have both final kinetic energies. Okay, from the conservation of momentum, since this is only in one-dimensional motions, so I'm gonna go directly to, okay, our initial is equal to the total momentum final. We have PAX plus PBX is equal to PAX prime plus PBX prime. This is one-dimensional X component. So next is we have MA, the mass of A, the velocity of A, X plus the mass of B, the velocity of BX plus the mass of A, the velocity of AX prime plus the mass of B, the velocity of BX prime. Okay. So if you look at the completely inelastic collisions, so it means that A and B have the same final kinetic energy, velocity. So meaning VAX prime is equal to VBX prime. We're gonna show this one as VX prime. Okay. So what will happen now is that MA plus MA VAX plus MB VBX. This is equal to, by the way, we're not able to read the problem. This is equal to uh, okay, M MA plus MB times VB X prime. Okay. So this problem if you repeat the collision described in the example 8.5, the previous problem that we answered, but this time they equip the gliders so they stick together when they collide. Find the final x velocities and compare the initial and the kinetic energies of the system. Okay. Okay. So this is our target variable. We divide both sides by MA plus MB. Can cancel. So therefore, your VBX prime is equal to your MA, which is 0.50 kilograms times the initial velocity plus the negative 0.30 kilograms times negative 2.0 meters per second over 0.50 kilograms plus 0.1. So how much should be that? Let's try to calculate. 0. Um, 0.5 times 2 plus 0.3 times negative 2 over 0.5 plus 0.3. So we have 0.5. So 0.50 meters per second into significant figures. Okay. So this is an elastic collisions, completely inelastic collisions, meaning they they actually have the same kinetic and they have the same final velocity. So if you actually calculate the kinetic energy here, okay, so we have the K1 is equal to K2, which is Ka plus Kb is equal to K2. Okay. So actually here the Ka is equal to of one half MAV. The initial is we calculated this one 1.0 joules and Kb is equal to 0.60 joules. But if K2, in terms of K2, the total this one, so the K2 is actually 0.10 joules. Okay. So we can see here that K1 is equal to 1.6 joules is not equal to K2, which is equal to 0.10 joules. Okay, so meaning some of the energies are lost. So so both the inelastic and the completely inelastic collisions, their kinetic energies is not conserved, only the momentum. So let's go to the elastic collisions. This the this is a bit harder than the previous two because it involves two conservation concept. Okay, so if you recall, okay, if you are going to recall, if you apply the conservation of momentum here in one dimension, so the final is equal to the initial is equal to the final plus. So here we can say that we have MA plus MB. Okay. So we can actually combine these two here. We can combine terms that they have common. We can transpose, and this one can transpose in the other side. So MA VAX minus MA VAX prime is equal to MB minus MA VAX prime. So actually, we can derive a formula for this that we can use, but I do not advise it because formulas are easily, especially the long formulas, are easily forgotten. Okay, so that's why you need to know how to derive formulas in dealing with elastic collisions. Okay, so here, what do you need here? So MA can is equal to VA x minus VAX prime. So prime meaning final, MV V Vx prime minus, okay, this is actually B. And this is not prime. Okay, I'm sorry. VBX. That's what. So this is our first equation. We get this one from the conservation of momentum. There's also a conservation of kinetic energy. Kinetic energy is conserved because this is elastic. So 1/2 MA VA X squared. This is only in one dimension plus 1/2 MV V Vx squared is equal to 1/2 MA VAX prime squared plus 1/2 MB VX prime squared. Okay. Can cancel this one. Cancel, cancel, cancel. And we have MA and we MA VAX squared plus MB VBX squared is equal to MA VAX prime squared plus MB VBX prime squared. So if we are going to combine like terms, we have MA just like this one, VAX squared minus, because we transpose this one to the other side, VAX prime squared is equal to, transpose this one to the other side, have MV VBX prime squared minus VBX prime x squared. Okay. So we have equation 1, we have equation 2. This is from the conservation of kinetic energies. Okay, are they related to each other? Okay, let's see. So use that a squared minus b squared is equal to a plus b, a minus b. Okay, so this term will become ma vax squared vx plus vax prime times vax minus vax prime become b bx prime plus b bx times b bx prime minus b bx. This is our equation. Let's just put this equation 2. Okay. So we have two equations that we can relate each other. Okay. Keep this. I'm gonna copy. Let's make this gun. Let's make this small. Okay, we have equation 1 and equation 2. From the equation 1, so we have MA is equal to MB. So, and equation 2 gives us that so let's now uh use equation 1 to put equation 1 to equation 2. Okay, instead of, so we let that this one, or this one and this one will become, this one and this one will become this one. So to cancel the other side. So instead of writing this one, so we have M from 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 1 uh, put into equation 2. So we have, instead of, so equation 2 becomes MV VB x prime minus VBX. Okay. In exchange for this one is equal to MB. Okay. So what do we have here? So we can cancel this one, this one, this one, this one. So we are left with as equation 3 as, so what does it mean? Okay. What does it mean, class? So what does it mean? How can we use this one? Okay. So we can actually combine BAX minus BBX is equal to VAX prime VBX prime minus VAX prime. We have here an equation number 4. So what is the use of that equation? Let's go to, so let's go to elastic collisions and relative velocity. Okay, if you don't know what's relative velocity, please review chapter 3. Okay, here we have the the initial velocity of A with respect to B is equal to the velocity of B relative to A. So we can actually write equation 4, the velocity of A with respect to B along X, this is equal to the VA minus VBX. This is actually equal to the velocity of B final minus the velocity of A. Final is the velocity of B with respect to A. Okay, final. Okay. So what can we say about this? Since in the relative velocity, the velocity of A with respect to B along x is equal to the negative of the velocity of B with respect to A along x, which is equal to which is equal to A minus B man siya, no? This one, x is equal to, from this equation 4, and we know that this one is equal to the negative velocity, which is equal to the negative velocity of B man siya gauna, okay? Velocity of B with respect to A, uh, this will become BBX minus VAX. So since this one is equal to this one, so we can equate these two here. Okay. The the velocity of B, the final velocity of B minus the final velocity of A is equal to the negative of the initial velocity of B minus the initial velocity of, okay. So may bot pasabot ani class the relative velocity. Okay, so relative velocity, this one, so in initial, if you look at this one, in the initial, after before the collisions, we have the, if we calculate the velocity of A with respect to B, the velocity of A with respect to B is equal to this one. So this is equal to this one. And this one is just the velocity of the final velocity of B with respect to A. Okay. So you can write this one. Since in our discussion in relative velocity, the this one the is equal to the negative of velocity of B with respect to A, which is this one. So therefore, this one is equal to this one, which is the, it states that the final velocity of B relative to A is equal to the negative of the velocity of B relative to the initial velocity of A relative to B. Okay. So in the elastic collisions, we have the conservation of momentum that we can use. So we have MA VAX plus MB VBX is equal to MA VAX prime plus MB VBX prime. And the other one, we can use that, it's actually said that in elastic collisions of the two objects, the relative velocities before and after collisions have the same magnitude but opposite sign. Okay. The VBX prime minus VA x prime is equal to the negative of VBX minus VAX prime x. So, so the relative velocities of the two objects has the same magnitude but before and after the collisions. Okay, so this equations here, you can use this one. I hope you review the relative velocity. You can use this one to answer. Actually, out of this, you can actually create a formula to determine the final velocities. This one, formula for this, formula for this. But like I said, I will not teach it to you because formulas are easily forgotten, especially in these days. You need to have a formula that is very easy to understand, very easy to remember or derive, just like this formula, two formulas that you're going to use in the elastic collisions. Okay, let's go to example 8.7. So we repeat the collisions in example 8.5, but now we add ideal spring bumpers to the gliders, so the collision is elastic. What are the final velocities of the gliders? Okay. Of course, okay, before we proceed, this one, there are two unknowns. So the first equation would not stand alone. It needs another equations to support it. So that's why we're gonna use first the initial equation. Number one, from the relative velocities states that the final velocity of B relative to the final velocity of A is equal to the negative of the initial velocity of B relative to A. And not gonna, okay. So meaning, we can actually, since this is given, so we have a given here. What are given here is this one. So we have the final velocities of B minus prime is equal to negative times the final negative 2.0 minus 2.0 meters per second. So we have negative 2 times negative 2 is equal, negative 2 minus negative 2 is negative 4 times negative is 4.0 meters per second. Okay. And from the conservation of momentum, we know that we have MA VAX plus MB VBX is equal to MA VAX prime plus MV VBX prime. Good. It's what it was from the conservation of momentum. Okay, what to do next? Okay, let's plug in the values. We have two unknowns. Okay, so we have, from this, we have 0.50 kilograms times initial 2.0 meters per second plus in this uh, 0.30 kilograms times negative 2.0 meters per second. This is equal to 0.50 kilograms times VAX prime plus 0.30 kilograms times VBX prime. Okay, what's next? So we multiply both sides by 1 kilogram or 1 over kilograms. 1/1 kilograms. So we can cancel the kilograms in all the equations. Okay. In the left-hand side, if you're going to calculate it, 0.5 times 2 plus 0.3 times negative 2 is equal to 0.4. So we have, so this left-hand side is 0.40 meters per second is equal to 0.50 kilograms VAX prime plus 0.3 kilograms VBX prime. And we have also another equations like this. 4.0 meters per second is equal to, gonna gonna put this like this, negative VA x prime plus VB x prime. Okay, so this is our equation 1, our equation 2, and equation 1. If we add this one, but before we add this one, let's multiply this one first to cancel out. Maybe let's multiply this one by 2. Equation 2 by 2. So this will become, equation 2 is 0.880 meters per second. If you multiply this one, so this will become 1.0. So it's already cancelled. This one is already cancelled, by the way. Because we multiplied it already. 1.0 BAX prime plus 0.6 B 0.60 B X prime. Okay. So we're going to add this equation here, equation 3 na ni, and equation 1. Okay. We add this one. Okay. This one and this one is equal to 4.8 meters per second. And this one is 0 plus this one plus this one, 1.6 plus BX prime. Okay, so therefore we can find that the BBX prime is equal to 1.6 is equal to, we divide both sides by 1.6, 4.80 meters per second over 1.6. So we get 3.0 meters per second. So this is equal to 3.0 meters per second. Okay, now okay, now we have to calculate what is this? Okay, we already have an equation. I think we have already equation like this. So from equation 1, okay, I'm gonna write here, write it. From equation 1, our BBX prime minus VAX prime is just equal to 4.0 meters per second. So since this is equal to equal to 3.0 meters per second, it follows that from here, VAX prime, transpose it from here, and this one transposed to the other side, we have 3.0 meters per second minus 4.0 meters per second is equal to negative 1.0 meters per second. Okay. So this is 1.0 meters per second. Okay. So we are able to calculate this elastic collisions with two unknowns with two equations that we use. The one is the concept of relative velocities and the concept of conservation of momentum. I hope you enjoy the lecture. So look at example 8.11 and try to use these formulas again. Example 8.11 so that you get you're gonna practice more. Okay? Time for 5 minutes break. 5 minute break. And see you in the next discussion. Okay, so let's go to two-dimensional collisions. So like what we discussed, there are three types of collisions: the elastic collisions, where some of the kinetic energies are lost. We also have completely inelastic collisions. Both have the same final velocities, and we have the elastic collisions where the kinetic energy is conserved. And also, we know that in any types of collisions, the momentum is conserved. Okay, let's discuss first what do you mean by interdimensional collisions. So, s- so since we are dealing with two-dimensional collisions, so we can in in conservation of momentum, so we can actually use the x component and the y component. So for the x component, so we uh, can actually ma. Uh, we have the px prime, px the is equal to px prime, and we have the p for the y component, py is equal to p prime y. So meaning we can actually use this one ma for example we have two vax plus mb vbx is equal to ma vax prime plus, and we can also have in the y component ma plus equal to ma va y prime plus mb vb y prime. Okay, so that's for the two-dimensional collisions. Okay, so here we have an example for the examples of the two-dimensional collisions. So we will not be able to actually know if this is an elastic collisions or inelastic unless we calculate the final energies and initial kinetic energies. But here, let's gonna answer what is asked. So 8.14 shows the two battling robots on a frictionless surface. Robot A, with mass 20 kilograms, initially moves at 2.0 meters per second, parallel to the axis. It collides Robot B, which is 12 kilograms and it's initially at rest. After the collisions, the robot A moves at 1.0 meters per second in the direction that makes an angle of 30 degrees with its initial direction. What is the final velocities of robot B? Okay, so we have actually, this is from the notations. Okay, we should erase this one. Okay, okay, let's go back. Okay, right now we're gonna use the two-dimensional conservation of momentum. So there's another annotations here that we're going to erase and that. Okay, so we already discussed the two-dimensional collisions. Okay, okay. So here we have B is at rest. A, okay. So from the conservation of momentum like this, we discussed. So from the X component, we have, okay. Let's calculate first the the x component. So here we say that the initial velocity, if we look at the initial velocity VA, so it has no y component actually, but it has an x component, which is actually it has a VAX, which is equal to VA cosine of 0, which is y is 0 because it is along the x, and it is since initially 2.0 meters per second times 1 is equal to 2.0 meters per second. That is our VAX 2.0. Our VBX initial is equal to 0, and our VAX is equal to uh, actually 2. It also has BAY, which is equal to 0. Since it is at rest, your BBY also is equal to 0. But we're gonna use this one first. So this is equal to 0. So VAX times MA is equal to MA VAX prime plus MB VBX prime multiplied by MA. Okay, your VAX is equal to, so what are we looking for this? What is our target variable? uh, what is the final velocity of robot B? So this is actually our target variable here. So not the A. So our target variable is this one. So we transpose this to the other side. So we have MA AX minus MA BAX prime is equal to MB BX. We divide both sides by MB. So your VB x prime is equal to VBX prime is equal to what? MA over MB times VAX minus VAX prime. For VB, so okay, VAX prime. Okay. So here we can clearly see that before we can answer this, we need to find first what is the VAX prime. Okay. And what is the VAX prime? Okay, if you look at this one, this is the final velocity with an angle of 30 degrees. Okay, if we zoom in this one, this is now our final velocity, okay, of our A in that direction. We have 30 degrees. Okay, it has a components VAX, which is equal to VA cosine of 30 degrees, VA prime. And it's also have the Y component, which is the VAY prime, which is the VA sine 30 degrees. So what is this? What is VA? What's the magnitude of VA? Okay, so robot A, so our VA here, so VA, so meaning our VA here is, VA prime is 1.0 meters per second, moves at 1.0 in the direction that makes an angle. So we have 1.0 meters per second cosine 30. So we have this one first. Let's see. Let's check our answer first. Okay. 1.0 cosine 30. Okay, maybe I'll just leave with that. And our VAY prime is equal to 1.0 meters per second sine of 30 degrees. Okay. So here we can actually, this is equal now to MA, which is 20 kilograms, and robot B is 12 kilograms times MA is 1.0 minus MA is equal to VAX, which is 22 meters per second, minus 1.0 cosine 30 degrees. So our VBX prime is equal to 20 divided by times 2 minus 1 times cosine 30. So we have in what is we have 1.89 meters per second. Okay. How about the y component? How to get the y component? Okay. So we have Vy is equal to 0 and the final is sine 30 degrees. Okay. So we have MA VAY plus MB VBY is equal to MA VAY prime plus MB VBY prime. Okay. So another, like if we said, this one is equal to 0 and our VAY has no y component. It's our VBY is no y component. Our VAY is equal to 0. Our VB VBY is equal to 0. Our VAX is pila ganito, 2.0. Our VBX is equal to 0 also. So initial, this is equal to 0. So we have this one. So we can get the MB VBY is equal to the negative of MA VAY prime. Okay. So we calculated that this one is just 1.0 sine 30 degrees. Okay, so VBY prime is equal to negative MA over MB VAY prime, which is equal to negative 20 kilograms times 12 kilograms times 1.0 meters per second sine of 30 degrees. You can actually get the value 1 times sine 30 degrees. So we have negative 0.833 meters per second. So now, we are able to get the VBX prime and the VBY prime. Okay. So if we, okay. So wait a minute. Let's put this, up for discussion. Let's put this up. Okay. So our results from the previous result is that we have our VBX prime is equal to 1.89. Our VBY prime is equal to 0.83 negative. If you graph that one, okay, if you graph that one, so the x is positive and the y is negative. So the vector lies on the fourth quadrant. Okay. And if you want to find this angle here, so what is the final velocity of the robot? So if this is we label this one as angle beta. If we want this direction, so the the tangent of the negative one is equal to the angle beta of the opposite. The opposite is the VBY, which is negative 0.833 meters per second over the adjacent, which is 1.89 meters per second. Shift tangent over 1.89. So the answer is into significant figures, negative 24 degrees. Okay, what does it mean? The direction, okay, it is negative 24 because it is read from the positive x-axis clockwise. Okay, clockwise, meaning the angle is negative. It is read from the diagram from the positive x-axis to the vector, read it clockwise. Okay. Or you can just put this one 24 degrees. Okay. What is this direction? This is the north. This is the north south. This is east and this is south. This is the south of west. 24 degrees. South of south of east. So that's how you answer that one. Okay. The most important thing here in two-dimensional collision is you just separate, apply the vector knowledge, and you're good to go. Okay. Another thing is two-dimensional completely inelastic collisions, just like example 8.9. So even though the lectures take long, but it doesn't matter because it is posted online. You can watch it every time you like. So let's answer these questions. Okay. So here we are dealing with an inelastic collisions. Okay, just like what we did, we separate. Okay, we have a 100 kilogram car traveling north at 15 meters per second, collides with a 200 kilogram truck traveling east at 10 meters per second. The occupants are wearing seatbelts, are uninjured, but the two vehicles move away from the impact point as one. The insurance adjuster asks you to find the velocity of the wreckage just after impact. What is your answer? Okay. You are asked here to find the final velocity of the wreckage. Okay. So for the x component, okay, for the x component, you have MA. So we treat this one as our A, and this is our B. So R, just this C, and this is our T for the truck. So the mass of the truck for the initial, and we have the velocity of the truck plus the mass of the car, the velocity of the car along x is equal to the mass of the truck, the velocity of the truck final along x plus the mass of the car times the velocity of the car times final. Okay, since this is completely inelastic, so we can say that the velocity of the truck along x is equal to the velocity of the car final along x. Is equal to just Vx prime. Okay, so mass of T plus the mass of this one will become the velocity of that one. Okay, we can also use for the y component. I mean, to finish this, so we divide both sides by mt plus mc, can cancel over mt plus c. Okay. So for the Vx prime, the final velocity along x, we have mt Vtx plus mc Vcx over mt plus c. Okay. So we have this is only for the x component. This is I just calculate the x component. So before we go there, okay. So what is so the truck is 2,000 kilograms. The initial velocity of the truck along x is 10 meters per second plus the car. So car is moving along y. So you look at the car. This is the velocity of the car. So the velocity of the car along x is equal to 0, but it has the velocity of the car along y is equal to 15 meters per second. In this particular case, the velocity of the truck along x is equal to 10 meters per second, and the velocity of the truck along y is 0. Okay. So here, we have here 1,000 kilograms times 0 over 2,000 kilograms plus 1,000 kilograms. Okay. So I can actually calculate the Vx prime here. Okay. It's equal to 2,000 times 10 over 5. So we have 6.667 meters per second. Okay. So what we get here is that the Vx prime. So if this is your V, we already get what is the component of that. If you want to find the Vy prime, so you need to calculate again. Okay. skip, erase. So for the y, so we have already sa x. So vy prime. Okay, so we have for the y component, we have we have m track, v v velocity track along y plus mass of the car, the velocity of the car along y is equal to the mass of the truck, the velocity of the truck along y prime, the mass of the car, the velocity of the car along y prime. Okay, so just like what we said, I uh, a moment a while ago, the velocity of the truck initial is equal to along y is equal to 0. But it has only the car has the velocity along y. Uh, After the collisions, okay, and the finals are the same. So we know that this one prime y is equal to the velocity of the car y prime is equal to just vy prime. Okay, so we have mt plus mc times vy prime, divide both sides by mt plus mc. So we can, your vy prime is now equal to mc v cy over mt plus mc. So we have the mass of the car, which is 1,000 kilograms. The velocity of the car, 15 meters per second along y. And we have 3,000 kilograms. So we have 5.00 meters per second. Okay. So we have Vy and Vx. So we can actually calculate now the magnitude of the velocity of the wreckage. So our Vx is positive and our Vy prime is also positive. So our velocity is in the second quadrant, just like in the picture. This is our velocity prime. Okay. So if you want to get the magnitude of this, of our final velocity of the wreckage, so we have actually from our equation 6.67 plus so we have 8.33 meters per second. That's our velocity of the wreckage. Okay, into significant figures, this is actually V is equal to 8.3 meters per second. Okay, if you want to find the direction, k theta is equal to the tangent of the opposite, which is the Vy, over the adjacent, which is the Vx. Shift, tangent. is equal to 37 degrees. Or this is equal to 37 degrees um, north of east. That's the direction. The magnitude is 8.3 meters per second. Okay, so the book has different solution for this example. Okay, but just basically the same concept. So we use the conservation of momentum. We separate the x and the y components. We get the vx and we get the vy, and we get the magnitude. And our answer is also the same with our reference book. In two-dimensional conditions, we have the elastic collisions, where we have discussed this one as the kinetic energy is conserved, and the kinetic energy is conserved, and the momentum is conserved. So here we discuss example 8.12 is a collisions with two-dimensional type of collisions, which is an elastic collisions in two dimensions. I'm going to discuss this one. Let's read the problem first. Okay, the two-dimensional elastic collisions. Okay, this figure 8.27 shows an elastic collisions of two packs given the masses MA and MB on a frictionless air hockey table. So pack A has an initial velocity of 4 meters per second in the positive x direction and the final velocity of 2 meters per second in the unknown direction alpha. Pack B is initially at rest. Find the speed v2 or the final velocity, the final speed of this pack B and the angles alpha and beta. Okay. Solution first is that you need to find first the final speed or the final speed of the pack B. Okay. You can use the kinetic energy. Okay. So the kinetic energies here are conserved. So meaning 1/2 A, the velocity of A, or the speed of A squared plus 1/2 the velocity of B, the speed of B squared is equal to 1/2 times the mass of A, the velocity of A prime squared, the final plus 1/2 MA MB, the velocity of B prime squared. Okay. What is the oh here we know that B is at rest. The initial velocity of B is 0. Okay. So what we also know that we have an initial velocity. So our target variable here is this one, the final velocity of pack B. The final velocity of A is given. So this equation is that the from the characteristic of an elastic collisions that the kinetic energy of the system initial is equal to the final kinetic energy of the system. Okay. We use this prime for the final values. In your book, we use 1 and 2. Okay. So since this is our target variable, so we can put this one into the other directions. So we can cancel actually this 1/2. So we have here the mass of V, the velocity of final velocity of V squared is equal to mass of A, the velocity of A squared minus the mass of A, the velocity of the final velocity of A squared. So we have M A, the velocity of A squared minus M velocity of B prime squared. Okay. So we have the mass, which is we have 0 point, okay, not yet. So we're gonna multiply both sides by the mass of B. So we're gonna cancel. Our PV now is equal to 0 0.500 kilograms over 0.300 kilograms times the final initial velocity, which is 4.0 meters per second squared minus the final velocity of A. So we got 0.5 over 0.3. Then we have 4 squared minus 2 squared. So we have 20. So we have 20. So cancel out meters per second squared. Okay. So the velocity of B prime is equal to the square root of 20 meters per second squared, which is equal to the square root of 20. So we have here that 4.47. So we're gonna use the sum digits to have an accurate results in the final results. 3, 4. Okay, this one. It's 4.47214. Okay, meters per second. This is the final speed or the magnitude of the velocity of our pack B. However, we need actually to find the angles alpha and beta, the direction of this A and B. What are the direction of A and B? Okay, to that we need to use the conservation of momentum. Okay, let's do along X. For the X component, this would really take time. So we have here M1 to MA VAX minus MV VBX. This is equal. So meaning the initial momentum, which is of A and minus plus initial momentum of B equals to the initial final momentum of A and B, which is equal to the mass of A, the final velocity of A, plus the mass of B, the final velocity of B. So here we know that the initial velocity of A is 0. Okay. So we are we are left with this one, initial, and this one. Okay. So here we have the mass of A, which is 0.500 kilograms times the initial along X. So along X, we know that this is, so if this is the velocity of A, so we know that the V, Vx is just equal, it's just the VA cosine of 0 is equal to 4 meters per second, because this is cosine of 0 or times 1, or just 4.0 meters per second. Your VAY here is equal to 0. Okay, so we have 4.0 meters per second, and our final velocity along A is just this, is just x. So if this is our final velocity in that direction, final, it has a components VA cosine of alpha, and also is equal to Vx. In the y component also, we have VAY equal to VA prime, VA sine of alpha. Okay, so we're gonna hit mass of A 0.500 kilograms, then multiplied by this one, this term here, which is, we know that this is the final velocity. We need to calculate this one, which is 2 cosine of alpha, which is 2.00 meters per second cosine of alpha plus this b here. So the b here is in this equation. We have beta, we have b, we have vb uh, prime cosine of beta is a vb prime x, and it also has a y component, vb prime sine of beta. This is b prime y. Okay. So here we have b is unknown, but we've calculated this one already, which is equal to 4.4724 214 meters per second, and we have the cosine of beta. Okay, we forget the mass, so maybe just gonna do this like this. Okay, plus, it's gonna add here plus 0.300 kilograms times 4.47 to 4 meters per second cosine of beta. Okay, this is for the y component. Okay, so for the y component, we have MA VAY prime, VAY plus MB VBY equal to MA VBY prime BAY prime plus MB VBY prime. Okay, so again, since B is at rest, this is equal to 0, and BAY, since since when we go back here, our initial, it has no it has no y component, so this is equal to 0. So we have 0 is equal to MA, which is 0.500 kilograms, and we have times the velocity of AY, which is 2.0 meters per second. Where is that? Here, 2.0 magnitude and the angle cosine. So now this is positive sine of alpha plus, since the component of this VBY here is negative, so VBY is actually negative. So we have plus the negative times the mass 0 point, or just gonna put minus 0.300 kilograms times 4.47214 meters per second sine of beta. Okay, so those are what we got from the conservation of momentum and from the our first calculations of getting the, what we call it one, the final magnitude of the final velocity of pack B. So from these equations, let's let that this one, let's multiply everything by 1 kilograms. 1 over kilograms. Or we can just delete the kilograms because the same thing here. 1 over multiplied by that. So we can actually delete this one, all the kilograms here and here. Okay. The next thing we do is that we let this one as to be this term as just the constant C. This is equals constant A. This is our constant B. And this is our constant C. And this is gonna be our this is our B and this is our C. Okay, so from that one we have two equations. A is equal to B cosine of alpha plus C cosine of beta. Okay. And from the second one, 0 is equal to B sine of alpha minus C cosine sine of beta. Okay. That's all we need. So from this one, you're gonna get this angle alpha and beta. Okay. We just made it simpler. Okay. So from that, so since we all have this one, we have equation 1, A is equal to B cosine of alpha plus C cosine of beta. So let's solve for cosine of beta here. And also for the next, so what we're going to do is solve for cosine beta here, sine for beta here, because cosine squared beta plus sine squared beta is just equal to 1. And then I'm gonna add this one. So we might able to eliminate uh, another variable, one of the variable. Okay, so to solve for cosine beta, so we have here, uh, we cannot transpose this another one to C cosine of beta is equal to A minus B cosine of min cosine of alpha over C cosine of beta is equal to A over C minus B over C cosine of alpha. Okay. So for the other one also, for equation 2, we have 0 is equal to B sine of alpha minus C cos sine of beta. It implies that uh, sine of beta is equal to, so transpose divide by C, B over C sine of alpha. So we have that too. So next is to square this one. Cosine squared of beta is just equal to A squared. So we're gonna actually, if you're going to square this one, you're gonna square that one. So cosine squared is just A over C squared minus 2AB over C squared cosine squared alpha cosine alpha minus plus plus B squared over C squared. So gonna write this one. A squared over C squared cosine squared alpha. And sine squared beta is just equal to B squared over C squared sine squared alpha. Okay. So if we add this one, okay, uh, cosine squared beta plus sine squared beta is just equal to this term here, a squared over c squared minus 2ab over c squared cosine alpha plus b squared over c squared, just cosine squared alpha plus b squared over c squared sine squared alpha. Okay, since this term here just is equal to b squared over c squared cosine squared alpha plus sine squared alpha, this is just equal to 1. Okay, so our final result would be, so this is also equal to 1. So we have, so from that equation, so we have 1 is equal to a squared c squared minus 2ab 2ab c squared, sorry, 2ab c squared cosine of alpha plus b squared over c squared. Okay, so we multiply both sides by c squared. So our final result would be c squared is equal to a squared minus 2ab cosine of alpha plus b squared. Okay, so from these equations, we're gonna transpose everything from here. So did we, I think this plus, this should be minus. They must, okay, okay, should be like that. So plus, okay. So if we transpose this one to the other side and this one to the other side, so we have negative 2ab. This one become positive. Cosine of alpha is equal to a squared plus b squared minus c squared over 2ab. So we're gonna have the cosine of alpha is equal to a squared plus b squared minus c squared over 2a and b. So what's next? We still have space. Gonna save this. Let's have more space. Okay, so what do we have now? What do we have so far? So we have derived that the cosine of is equal to a squared minus plus b squared minus c squared is equal to 2 times a b. So if we want to get the alpha is equal to the cosine to the negative 1 of a squared plus b squared minus c squared over 2a b is just equal to cosine to the negative 1 of what is a. So let's go back here. So from here, a is just equal to 0.5 times 4, 2 is equal to just 2 meters per second. Okay, a. And b is just equal to 1 meters per second. And c is just equal to 0.3 times 4.47 to 1 point around 1.341642. Okay. So here, and so a is equal to 2 B is equal to 1 meters per second. Uh, C is equal to 1.34164 meters per second. Okay. So here we have 2 meters per second squared plus 1. So I did not minus 1.34164 squared over, so this a close parenthesis, 2 times 2 meters per second times 1 meters per second. Okay, so every unit will be cancelled out. What are left? So we have alpha is equal to, so let's do the calculation. Plus 1 squared, 2 squared plus 1 squared minus 1.34164 squared over 2 times 2 times 1. So we have here 38, 36.8687 meters per second. In three significant figures, this is equal to 36.9 met this one degrees. 36.9 degrees. Okay. How about finding the beta? Can you find the beta? So to find the beta, maybe we're gonna use this term here. So to find the beta, we have, uh, we're gonna use this one. Sine beta is equal to B over C sine alpha. Okay. Sine of beta is equal to B over C sine of alpha. Since we know what's alpha, so beta is equal to sine -1 B over C. What is B over C? B is just equal to 1 over 2 meters per second. Cancel, cancel. We have 1 sine of 36.9. This one, 36.9 sine to the -1, 0.5 times sine of 36.9. Okay, I must have missed something. This is, by the way, B and C. Okay, sorry. This is B, 1 meters per second, and the value of C is, let's make this long, 1.34164 meters per second. So we have 26.6 degrees. So that's how to do the two-dimensional elastic collisions. So if you have, so you'd better practice this kinds of problem. So this is the end of collisions discussion for the collisions. So let's have a 5-minute break. So coming up is the center of mass. So now we're going to discuss the section in this chapter. It's called the center of mass. Okay. Suppose you have a several particles with mass m1, m2, and so on. Okay. So in a system, there are several particles with masses, just like this oxygen here. It has 3 masses. we have an mass of the oxygen and the two hydrogen. We have overall three masses. Okay. We note this on M1, M2, and M3. Okay. And we let that the coordinates of M1, for example, is 0, 0, which is Y1, X1, and those M2, and so on. So this is a systems of particles with masses. So we let that there are systems of many particles with positions. Then we define the center of mass of the system as a point that has coordinates x center of mass, y center of mass given by this equation. Okay, to find the center of mass along x is equal to m1 x1. So the mass 1 and the position plus the mass 2 and the position of mass 2 plus the mass 3 and the position of mass 3. If there are a lot of particles, then plus that. This is the summation of that over the M1 plus M2 plus M3 plus that. This is the summation of that. Also the same for the Y component. In vector form, we can see that the center of mass of the system of particles is equal to R center of mass. This is equal to the position vectors of individual particles times their masses over or just the mass weight average of the positions R1, R2 of the individual particles. So this is the formula. Okay. How about the center of mass for the homogeneous objects? Okay. For the homogeneous objects, the center of mass is where the center of mass is located, or the geometric center is if an homogeneous object has a geometric center, that is where the center of mass is located. It's like this cube. Oh, the geometric center of the cube is in this position, so that's the center of mass. The sphere is in the very center of the sphere, also for the cylinder. Okay. If an object has an axis of symmetry, the center of mass lies along it. Okay, just like for example for the disk. How about the donut? As in the case of the donut, the center of mass may not be within the object, but it can also it is in the axis of symmetry. Okay, that's the center of mass of the donut. It doesn't have to be in the body, part of the body. Okay, this is an example for the center of mass. So like what we said, this is the water molecule, systems of particle with masses and different positions. So shows the simple model of a water molecule. The oxygen-hydrogen separation is D equal to 9.57 times 10 to the negative 11. So each hydrogen atom has the mass this one, and the oxygen atom has the mass of this one. Find the position of the center of mass. Ito ano na to ang position of the center of mass. Okay. So here, from the formula that we have discussed, from X, for example, this is just equal to M1 X1 plus M2 X2 plus M3 X3 over M1 plus M2 plus M3. Okay, that's the formula. Okay. So given that, okay, so if we let this one as our M1, this is our M2 and M3. So the positions of M1, okay, for example, the mass M1 is the oxygen with atomic mass of 16U. Then we have the 16 times the position, which is in the coordinate 0, okay, plus, okay, the positions of M2. Okay, if we look at M2 here, along X, this is just equal to, if this is D, this is equal to D, and if this is 105 divided 2, So 52.5. So if we look at this one, this is our M2. So here is 52.5 degrees. And this location here is this is the X for the M1. This is also here is also 52.5 degrees. Okay. Okay. So the location of the location of the mass to is just x2 is just equal to, since this is equal to d cosine of 52.5 52.5 degrees. Okay. So here we have the mass 3, which is equal to 1.0 atomic mass unit, and we have times d cosine 2.5 degrees. Okay. And plus, we need to plus this one, 1.0 u plus, since this is also positive for the mass M3, uh, d cosine 52.5 degrees. This is 52.5 degrees. Okay. This is over 16 plus the mass of M1, M2, and M3. Okay. Since this is equal to 0, so, okay, calculate this one times cosine and the other one over, okay, so we have here for the x 0.067 or 68 d. Okay. 0.68 d, where d is equal to this one. Okay. How about for the y center of mass? So again, so we have positions for M1, 16.0 u times 0 plus, we also have 1.0 u times our M2. The position of our M2 is positive. Our Y2, this is Y2. This in this level. So we have Y2 is in that level, but Y3 is negative in that level. So Y2 is, so this is positive D, now sine 2.5 degrees plus, however, our Y3 here, this point, Y3 is negative. So negative D sine of, so the mass first, 1.0 times negative D sine of 52.5 degrees over 16 0 u plus. Okay, since this one is 0 plus this one is equal, plus this one will be just add 0, then the y center of mass is equal to 0. So the center of mass for this molecule is somewhere 0.58 times d. Okay, so you can locate the center of mass. So if you substitute, so it is along x, the x center of mass is equal to 0.068 times 9.57 times 10 to the negative 11 meters. Okay. times 6.5 times 10 to the negative 12. So that is the location of the center of mass. So it must be positive. Kung positive, so it's somewhere like right here, the center of mass of that. So let's go to the motion of the center of mass. Okay. So since the center of mass is given by r, okay, and the derivative of, so since if we do this, okay, so for example, we have, for example, in the x, derivative of this one over dt, the change of that, the small change of that over dt is equal to m1 dx1 over dt plus m2 dx2 over dt plus that over m1 plus m2 plus m3. So what will happen? This will become v, this will become v center of mass along x, okay, r center of mass, or this is just x, dx center of mass. So this is just equal to, so the v center of mass is equal to m v1, m1 v1 along x plus m2 v2 x plus that over m1 plus m2 plus that. Okay. So also the same for y. So therefore the velocity v center of mass, okay, or the center of mass moves as though all the masses were concentrated at that point, is just equal to this one. Okay. So if you let that, this one, this term here is just equal to m, and we multiply both sides by m. Okay. So now we're gonna get the total mass of the systems of particle, the total momentum of the system. So the total momentum of the system is just equal to mass, the total mass of the system of particles, which is given by this one, multiplied by the velocity of the center of mass, which is equal to the momenta of the individual particles, just like that. So this is the motion of the center of mass. Okay. So what happens if, so we can also define the acceleration, okay, around the center of mass is equal to m1 a1, okay, plus m2 a2 plus that over m1 plus m2 plus that. So if we let this one as m, we multiply both sides by m, okay, we have m a center of mass is equal to m1 a1 plus m2 a2 plus that. Okay. Now, this first term here is equal to the vector sum of all the forces of the first particle. Okay, and so on the right side. So this equation here is equal to the vector sum of all the forces on all the particles. Just as we did in the 8.2, we can classify each forces as the external or internal forces, the sum of all the forces along x. Okay, so since we the net force, okay, sa system, there is an F external plus the F internal. So this is equal to the M over A center of mass. However, Newton's third law states that all internal forces cancel in pairs. So therefore, this one is equal to 0. Okay. Therefore, what's our left? That the net external force on an object or a collection of particles is equal to now, therefore, equal to the mass times the A center of mass. Okay. Is equal to the total mass of the object or the collection of particle multiplied by the acceleration of the center of mass. Okay. If the net external force on a system is 0, do you think the the center of mass velocity VCM is constant? So of course, so we have A center of mass is just equal to M dV center of mass over dt is equal to the net external force. If this is equal to 0, therefore dV Cm is equal to dt is equal to 0. So meaning VCM or the V center of mass is constant because the derivative of that is equal to 0. So that's what we mean. Okay. So we have here the problem. It's 8.14, the tug of war on the ice. Okay. So James mass is 90 kilograms and Ramon is 60 kilograms. They are 2 meters apart on the frozen pond. Midway between them is a mug of their favorite beverage. They pull on the ends of a light rope stretched between them. When James has moved 6.0 meter towards the mug, how far and in what direction has Ramon moved? Okay, again, when James has moved 6 meters towards the mug, how far and in what direction has Ramon moved? Okay, so the initial coordinates of James and Ramon are negative 10 and positive 10 respectively. So the coordinates of the center of mass is, so let's find the coordinate of center of mass first. X, center of mass. We need to know where is that from the origin. Okay, so we have this is our M1 and this is our M2. So M1 is 90.0 kilograms. This is around negative 10.0 meter plus 60.0 kilograms times positive 10.0 meter. Okay, over 90.0 kilogram plus 60.0 kilogram. So our answer is around negative 2.0 meter. So when James moves 60 towards the mug, okay, James moves 6.0 meters. So James moved, so so this is this is negative 2. So 1, 2. The new coordinate is negative 4.0. Okay. How far and in what direction has Ramon moved? Okay. Okay, dipole lines and the lines between them when James has moved. Okay. When James is moved towards this new coordinate is negative 4.0 because so if he moves 6 meters, so James is now in negative 4.0 meters. Okay. So well, can Ramon's new coordinate x2, the center of mass doesn't move, so so if the center of mass is the same, how far in what direction has Ramon moved? Okay. So kung si James moved 6.0 towards the mag, how far and in what direction has Ramon moved? Okay. The new coordinate is negative 4.0. Okay. And well, we'll call Ramon's new coordinate at x2. So let's call the new coordinate of Ramon as x2. We don't know that. Okay. The center of mass must, if the center of mass is the same, so what would be the x2? Okay. Okay. So here, x center of mass is equal to negative 2.0 meter. This is equal to 90.0 kilogram, and the new negative 4.0 meter, okay, plus 60.0 kilogram times x2 over 150, or 90.0 kilograms plus 60.0 kilograms. Okay, what is now x2? If you do the calculations, x2 is just equal to, so we do the math, we multiply this one right here, and then we forward and divide by this one. So you're gonna get 1.0 meters. Okay, 1.0 meters. So if if James has moved 6.0 from this one, so this is the new coordinate, and if the center of mass remains in this position, the 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 new position of Ramon should be around 1.0 meter to maintain the center of mass of that to be in this direction. Okay. Okay. So let's have a break first.